Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion. We will be looking today at Chapter 10 in a Student's Guide Through the Great Physics Text, Volume 2. In this chapter, we explore the relationship between equilibrium, force, and acceleration, along with Galileo in his dialogues concerning two new sciences. If you jump to page 133, there's a discussion of what they're going to be talking about in this chapter. I'll read a couple of sentences here to give you a flavor of what's going on. The above corollary has been proven for the case of vertical fall, that is, the corollary that they were just talking about, namely that an object undergoing falling motion or a falling object acquires equal increments of speed in equal increments of time, that is, it's undergoing uniform acceleration. He goes on to say, but it also holds for planes inclined at any angle, for it is to be assumed that along these planes the velocity increases in the same ratio, that is, in proportion to the time, or, if you prefer, as a series of natural numbers. So this is something that we talked about at the end of the last chapter, that if you let an object slide or roll down a plane, if we can ignore friction, which is a dubious assumption I might add, but in the event that we can ignore friction, that object will undergo uniform acceleration. The acceleration might not be as large as it was for a falling object, but nonetheless it will undergo uniform acceleration. This is what Galileo tested with his balls rolling down ramps. And here we pick up the dialogue. Salviati begins by saying, "Here, Segredo, I should like, if it be not too tedious to Simplicio, to interrupt for a moment the present discussion in order to make some additions on the basis of what has already been proved, and of what mechanical principles we have already learned from our academician." Remember, the idea is that they are reading a book by an academic and they're discussing this book. This addition I make for the better establishment on logical and experimental grounds of the principle which we have above considered, and what is more important, for the purpose of deriving it geometrically, after first demonstrating a single lemma, which is fundamental in the science of motion. So Salviati is going to go on and prove something regarding uniformly accelerated motion. Segredo then chimes in and says, "If the advance which you propose to make is such as will confirm and fully establish these sciences of motion, I will gladly devote it to it any length of time. Indeed, I shall not only be glad to have you proceed, but I beg of you at once to satisfy the curiosity which you have awakened in me concerning your proposition." And I think that Simplicio is of the same mind. Simplicio says, "Quite right." Okay, then Salviati, again representing Galileo, goes on to say, "Since then I have your permission, let us first of all consider this notable fact, that the momenta or speeds of one and the same moving body vary with the inclination of the plane." Okay, and now in the next paragraph, he goes on to explain what he's talking about. So if we jump ahead to the next page, he talks about a plane. Think about a ramp, a plane FA. And if you allow an object to roll down this plane or slide down this plane, it will undergo, he claims, uniform acceleration. But if you were to make it a larger incline, EA, or perhaps DA, then it will also undergo uniform acceleration, but the acceleration will be greater. And then finally, if you get it to become a vertical plane, BA, you have the case of a freely falling object, and it will undergo uniform acceleration, but it will have the largest of those uniform accelerations. Now, the question is, what is the relationship between the accelerations along these different planes? And here, if we go to the top of the final paragraph on the bottom of page 134, he makes a claim. He says, "It is clear that the impelling force that is acting on a body in descent is equal to the resistance or least force sufficient to hold it at rest." In other words, when something is rolling or sliding down the plane, he's claiming that there's a force that's causing it to do so. And the force that it experiences in going down the plane is exactly equal to the force that it would have taken to support this object stationary or in equilibrium on the plane. So in other words, if it takes a big force to hold something up, then when you release it, it experiences a big force that is trying to accelerate it down the plane. If, on the other hand, it takes a small force to hold something up, then it takes a small force, it feels a small force and hence a small acceleration going down the plane. So in other words, he's going to claim that the acceleration that a body, think about the body G in this diagram, the acceleration that this body G experiences when released is going to be proportional to the force that was formerly required to support it. You might remember there's something about this that he talked about earlier. He was talking about when you have balls that are being supported in a fluid. You might recall that if you had a column of air and you held a ball in this column of air, like this, and you were supporting it with some force. That's the force that it took to hold this up. Then if you were to cut this string, then the object would undergo a certain acceleration as it fell. But if you were to take the exact same object and instead of hanging it in a column of air, you were instead to suspend this in a column full of water, well then, because of buoyancy, it would take a much smaller force to hold it up. And as a result, if you were to cut the string that's supporting it, it too would accelerate downward, but the acceleration would be much smaller. So in some sense, the acceleration that an object feels when dropped, he is going to argue, is proportional to the force that it took to hold it up. Now, the question we must ask is how much force is required to support a mass that is resting on a ramp? In order to address this question, we're going to have to go back in time and look at the work of a man named Simon Stevinus. Simon Stevinus was a scientist and a mathematician who wrote a book called The Art of Weighing. He lived between 1548 and 1620. And in this book, he presents a now famous diagram, which is sometimes called the Epitaph of Stevinus, because apparently it appeared on his gravestone. What is the point of this Epitaph of Stevinus? Well, the point is to demonstrate that the 4 beads that lie on the left of this ramp are exactly balancing the 2 beads that lie on the right of the ramp. Let me explain in a bit more detail. What is shown here is a ramp A, B, C, D. And you have a string of beads. These beads are wrapped over the top of this ramp so that exactly 4 beads fit on the left ramp, AB, and 2 beads fit on the right ramp, and they're connected under the bottom by 1, 2, 3, 4, 5, 6, 7, 8 beads. And the claim that he makes is that the 4 beads on the left are just right to balance the 2 beads on the right. How do we know that those 4 beads on the left balance the 2 beads on the right? That is, this string of beads will not rotate around either in the clockwise or the counterclockwise direction. Well, he says if they did not, let's say for example that the balls on the left caused this to rotate around in the counterclockwise direction. That is, the 4 balls on the left, suppose for the sake of argument that they're a little bit heavier and they cause this thing to rotate in the counterclockwise direction. Then it would rotate. But after a short rotation, ball P would fall off the end and move over to the position where ball O is, and ball E, which is over the top, would move up to where bead D had been, and you will have the exact same situation as you had before, with 4 beads on the left and 2 beads on the right. And if that was not balanced in the previous moment, then it will not be balanced now, and it will continue to rotate around to the left. And so the bead that is then at P will again fall over to O, and the bead that's over on the right at the new position E will be up at position D, and it will continue to rotate. In other words, after a short rotation, it would look the same as a moment ago, and it would continue to rotate. And then he argues that since perpetual motion is not possible, the 4 balls must balance the 2 balls on the right-hand side. Now, we could get rid of the unnecessary 1, 2, 3, 4, 5, 6, 7, 8 balls on the bottom. If that's the case, we would redraw this in the following way. We would just have point A, C, and B. Notice that these 8 balls at the bottom don't play any role because they're symmetric in the left-right direction. So we could instead cut those off entirely and consider only the 4 balls on the left and the 2 balls on the right that are connected by this chain, like this. And since those 8 balls underneath don't play any role, we must again have the 4 balls on the left balancing the 2 balls on the right. Okay? But there's nothing really special about these being balls, really. We could, instead of having 4 balls and 2 balls, we could have instead just had 2 masses. So I'll redraw it once again, A, B, and C. We could have had a little pulley right here, and we could have had a mass of 4 right here, and a mass of 2 right here, connected by a string, and that too should be in equilibrium. That is, a mass of 2 balances this mass of 4. Okay? And now notice also that the whole reason that 4 beads fit along this ramp and 2 beads fit along this ramp, since the beads were equally spaced, is because this ramp side has a length of 4 compared to a length of 2 over there. So notice that the masses required to maintain equilibrium are related to the lengths of the ramp, to the lengths of the sides of the ramp. So because this ramp has a slope given by the length of this side being 4 and the length of this side being 2, then a mass of 4 must exactly balance a mass of 2. This follows from the considerations of the Epitaph of Stevinus. In other words, the weight more generally, if we were to have some ramp that had a length LA on this side and a length LB on that side, and you were to want to know what masses you have to have over here and over here so that they're in equilibrium, we'll call this weight A and weight B, attached by a rope. For equilibrium, one must have that the weight of block A is to the weight of block B in the same ratio as the length of A is to the length of B. This is the case for equilibrium. So Stevinus has provided us with a clever proof for finding out what weights are required to hold another weight in balance on a particular ramp.